Welcome to my videos. Uh, in the last session, I discussed about the transducers. See, in this session, I'm going to explain about uh, strain gauge, transducers. See, uh, strain gauge construction and working, and the semiconductor strain transducers, and potentiometric transducers. After completion of this video, you will be able to know about strain gauge construction and working, and construction and working of semiconductor strain gauge transducer, and the working of potentiometric transducer, its advantages, disadvantages, and applications of each transducer. Before entering to the session, just we will recall the previous sessions. See, in the last session, I explained about transducer. What is a transducer means? Transducer is a device. It converts one form of signal to another form. Generally, the output is in the electrical signal, and the input may be either mechanical signal or any other physical parameters. Or that means a transducer is a device. It converts any physical parameters or mechanical vibrations into the electrical signals, right? This is about transducer, and also we discussed about the classification of the transducers based on the this output. The transducers are mainly classified into two types: active transducers and passive transducers. See, what is a passive transducer? The name itself it is specifying passive, right? That means the output may be either in the output parameter is either resistive, capacitive, or inductive. That is passive transducers. And the active transducers are piezoelectric transducers, solar cells, like that. Right. This is about the classification. Again, in the passive transducers based on the parameter resistive transducers, capacitive transducers, and inductive transducers. Right. And construction and working of the wide strain gauge also we discussed in the previous session. See, wide strain gauge based on the applied stress, the strain it will be varied. The resistance will be varied. It is a resistive passive transducer. It is a passive transducer, and the main element here is a component is a resistive. So that means based on the applied stress, the resistance will be varied. This is about the wide strain gauge. So in this session, we will discuss about the foil strain gauge transducer. Foil strain gauge, right? See, strain is sensed with the help of a metal foil. There is a metal foil. Now that the strain is applied. See, foils are metals and alloys. What is a foil? Here, foil may be either a metal or alloy, like nichrome and tungsten, etc. See, much greater dissipation than wide gauges because larger surface area. The dissipation is very high in this foil strain gauge compared to the wide strain gauge because of larger the area is very high. Right, and compared to the wide gauge, the surface area is high in this foil strain gauge. Because of that, greater dissipation will be there. It can be used for higher operating temperature ranges. So that means it is generally it can be used for to operate high temperature ranges. The temperature range of foil strain gauge is high compared to the wide strain gauge. Larger surface area leads to better bonding. The bonding will be more in this foil strain gauge because of larger surface area. We will see the construction of this foil strain gauge. In this foil strain gauge, first a layer of strain sensitive material is bonded to a thin sheet of paper. See, foil strain gauge, right? In this, a layer of sensitive material is bonded to a thin sheet of paper or bakelite. First, that means on a paper or bakelite, a layer of very sensitive material is bonded on this. The portion of metal used as strain element is covered with the masking. See, here where this metal is, that means see here in the strain gauge, it is a resistive type. So a conductive material will be there. That means a portion of the metal whatever we require to apply on the strain, that is covered with masking. Right after masking, the so etching will be processed. With that etching, whatever may be the masked portion, unmasked portion, that will be removed after the etching. The etching solution is applied. See what is happening in this foil strain gauge. First, a thin paper is taken, thin sheet of paper. On that, whatever may be the sensitive material we need to use for the foil, that may be bonded on this sheet. After that, whatever on the required part of the metal, there will be a masking is provided. The next step is this sheet is placed in a etching solution. So we know that what is etching. With this etching, whatever may be the uncovered part, that will be removed. That means this etching process removes the unmasked portion. That means after etching on the paper sheet, on the sheet, only the masked area will be, masked metal is provided. Masked metal. See, finally, desired grid structure is achieved. Whatever we needed, that is on the paper, remaining will be removed from the sheet. See, we know that strain gauge, gauge factor. Generally, the strain is based on the gauge factor only. It is the ratio of change in resistance to the change in length. See here, we can see the foil strain gauge. Foil strain gauge. Suppose this is the thin paper. Consider this is the foil metal, right? See there, that means before my etching, this area or the required area is covered with masking, and after etching, the uncovered area will be removed. Only the covered metal area is available. Now, finally, the foil strain gauge will be like this. Here the gauge factor is change in resistance delta R by Rg to the epsilon. Epsilon, what is epsilon here is the strain. Or we can change another formula is change in resistance to change in length of the wire. See, here what is Rg? Rg is the resistance of the underformed gauge. Underformed gauge. G is indicating underformed gauge. And what is delta R is a change in resistance caused by strain. Change in resistance, and then that means based on the strain, the resistance is varying. So delta R is a change in resistance caused by strain, and epsilon is the applied strain. Epsilon is the applied strain. So gauge factor is change in resistance delta R by Rg divided by epsilon. Typical foil strain gauge, generally the strain gauge structure will be like this. See, here the gauge is far more sensitive to strain in the vertical direction than the horizontal direction. This is the strain gauge, foil strain gauge structure. Here the applied strain is more sensitive on the vertical direction than in the horizontal direction. See, here you can see these are the terminals, strain, sensitive pattern. And this is the area where we will apply, the strain will be applied. See, near areas, if you here observe this, near areas, that means here, that means area will be narrow. Area is narrow means resistance increases. We know that R equals to rho into L by A. So inversely proportional. Area is inversely proportional to the resistance. The area is increases means resistance decreases. So here area is decreased, narrow area. That means resistance increases. For lower resistance, if that means the thickness of the area is increased. That means the resistance decreases. What are the advantages of foil strain gauge? They can be fabricated on a large scale integration. This large scale, the fabrication is possible on a large scale. They can be fabricated in any shape based on, that means it can be the required shape we can fabricate. The foil can also be etched on a base. Base etching can be provided. Next one is the semiconductor strain gauge. Semiconductor strain gauge. See, already we know that semiconductor. Semiconductor is a type of material. The conducting is semiconducting. Alright. Already we know that the silicon and the germanium are the mainly used semiconducting materials. See, what are the advantages of semiconductor strain gauge? Already we discussed wide strain gauge and the foil strain gauge. Now here now we are discussing about the semiconductor strain gauge. See, what are the advantages of it? See, semiconductor strain gauge, the gauge factor is high. High gauge factor. This allows measurement of very small strains of the order of 0.01 microstrain. See, semiconductor strain gauges are used to measure very small strains. Very small strains, that is in the order of 0.01 microstrain. That means, and these are most very useful for to measure the small strains. The gauge factor is high and it can be used for to measure very small strains. His characteristics are excellent, right? Frequency response is up to 10 power 12 hertz. The frequency response is very high. Small in size, size is less. See, what are the features of semiconductor strain gauge? The size is small, less size, but high gauge factor. Okay, it is used to measure very small strains, and the frequency response is 10 power 12 hertz. What is the principle of operation of this semiconductor strain gauges? It works on piezoresistive effect. It works, semiconductor strain gauge works on the piezoresistive effect. Means change in resistivity of semiconductor due to strain and leads to change in resistance. The semiconductor resistivity is varying due to the applied strain and it leads to the change in resistance. That is the main principle of this piezoresistive. No change in dimensions when strain. Previously, what we discussed with the applied strain, the area or length of the wire material will be varied. Based on that, the resistance is varying. But whereas in the semiconductor strain gauge, no change in dimensions when strained. That means the length of the material or the area of the material is not at all changing. Only the resistivity of the semiconductor material is going to change in this semiconductor strain gauge. See, this is the structure of the semiconductor strain gauge. See here, this is the semiconductor. The resistivity of the semiconductor varies based on the applied strain. These two are the electrodes. This is the base, and these are the gold leads. And these are electrodes. See here, the gauge factor is already we discussed. What is the gauge factor? It is the change of resistance delta R by R to the strain. The gauge factor is very high in this semiconductor strain gauge. Germanium and silicon are the used materials here. Gauge consists of semiconductor crystal material of thickness 0.05 mm. The gauge of this material is of 0.05 mm. Bonded on suitable insulating substrates such as Teflon. This material is bonded on a insulating materials. Generally, it may be Teflon. Leads are placed in a protective box. Already just now is a gold leads. These are placed in a protective box. Generally, gold leads are employed. These are the features construction of this semiconductor strain gauge. There will be gold leads, and the material may be either germanium or silicon. And the gauge of this material is of thickness of 0.05 mm. Generally, these are used. The material, insulating material is Teflon. On this material, it is bonded. What are the disadvantages of this semiconductor strain gauges? It is very sensitive to change in temperature. The main disadvantage is here, it is very sensitive to change in temperature. Temperature variations are more in this semiconductor strain gauge. That is the one of the major disadvantage of this semiconductor strain gauge. Linearity is poor and more expensive. Difficult to attach to the object under study. It is very difficult to attach to the object under study. Right? Whatever we need to measure, that is difficult to attach to the objects. These are the disadvantages of semiconductor strain gauge. What are the advantages means? High gauge factor, it is used for to measure very small sensitive strains, right? And the size is small. Hysteresis characteristics are good. But what are the disadvantages? Temperature variations are high and the linearity is poor. Size is small, but it is very expensive because of gold leads and all these things. So this is about the semiconductor strain gauge. Next, we will discuss potentiometric transducer. See, it is also a transducer, potentiometric transducer. Potentiometric transducer is a type of passive transducer, an electromechanical device. Already we know potentiometers. It is used to, right? Generally, variable resistor. You use it as a variable resistor. Right? Here it is a passive transducer and it is an electromechanical device. A variable resistance transducer. Potentiometric transducers are variable resistance transducers. We will see the construction of this potentiometric transducer. It consists of a resistance element provided with a sliding contact. There will be a resistive element, and there is one slider is provided on this resistive element. Based on this, varying this slider, the resistance will be varied. That is the reason it is called variable resistance transducer. Variable resistance transducer consists of a resistive element with a slider. Sliding contact is called here wiper. The slider is called wiper. By varying that wiper, the resistance of that will be varied. Wiper may be translatory or rotary according to the design. That means this wiper can be provided in two ways. That may be either translatory wiper or rotary wiper. We'll see different types of potentiometric transducers. These potentiometric transducers are classified into rotational type, linear type, and helipod. There are three types of potentiometric transducers. Those are rotational type, linear type, and helipod. Working principle of this potentiometric transducers. In this, the resistance element is excited with DC or AC voltage. Generally, what is the potentiometric? There will be a resistive material, and this is wiper will be provided. This resistive element is excited with either a DC or AC voltages. Motion of wiper results in a resistance change. This material is exciting with DC or AC, but here this motion of this wiper is changing in the resistance. Change may be either linear, logarithmic, or exponential. Yes, change in resistance may be either linear, logarithmic, or exponential. Type of change is dependent on the manner in which wire is wound. How this resistive element is wounded. Based on that, the type of change, that maybe this change may be either linear, logarithmic, or exponential. It depends on the why is wounded on the resistive material. Different types of potentiometric transducers, right? Resistive displacement sensors. Resistive displacement sensors. Here you can see this is a resistive material and there is a wiper provided on this wiper. By varying this wiper, the resistance can be increased or decreased. See how what is the delivered output here we can see. This is the provided voltage, Vs source voltage. An electrically conductive wiper slides against a fixed resistive element. There is a fixed resistive element, wiper is there. To measure displacement, generally resistive displacement sensors. To measure displacement, a potentiometer is typically wired in a voltage divider configuration. Here the principle is voltage divider configuration. Here And known voltage is applied to the resistor ends. This is the known voltage applied to the resistor ends. The contact is attached to the moving object. Generally, this wiper is attached to the moving object. That means whatever we need to measure the displacement. This is attached with this wiper. The output voltage at the contact is proportional to the displacement. Based on the displacement, this wiper will be varied. That means this output V0 is the output is depends on the proportional to the displacement. Here, what is V0? Output voltage with the voltage divider principle. What is that? Voltage applied voltage, that is Vs into the resistance x minus x minimum. Here x is the distance between the varied wiper. Then x minus x minimum divided by x max minus x minimum. X max minus x minimum total resistance. Right? V0 equals to Vs into this x minus x minimum by x max minus x minimum. This output is proportional to the displacement. Proportional to the displacement. Based on the displacement, this wiper varies. Based on that, the resistance will be varied. That means the output also varies. This is the principle of this resistive displacement sensor. Another type is translational potentiometer. Translational potentiometer. See here, this is the wide wounded applied voltage, input voltage, and our output voltage here. This is the wiper. This is the wiper. On the insulating part, this resistive element is wounded. It is used for translatory displacement. Previous one is resistive displacement. Resistive displacement. Here it is translatory displacement. And then next one is a rotational potentiometer. Rotational potentiometer. Here this is the resistive material, right? And the wiper. This wiper is varied. Wiper can be moved rotationally, right? Here the output voltage. Output voltage is with the points between A and B. So B is the fixed one, A is the varied resistance. It is used for measurement of angular displacement. Angular displacement. Helical resistive element. See here, it is in the previous one, it is single turn rotational. Here, helical is multi-turn rotational device. It is used for measurement of either translatory or rotational motion. Both measurements, translatory motion or rotational motion, we can use this. See, helical multi-turns. There are more. You see here, you can see multi-turns. Helical shape. The shape of it is helical. It is heliport. Applied input voltage is between the first and then the starting and ending ends of the material. See, this is the wiper, and the output voltage is between this starting point and the wiper movement. Used for angular and rotational motions. Measurement of displacement. Already we discussed. See, this is resistive displacement. The object, whatever we need to measure the displacement, that is attached to the wiper. This is a V0 moving object. The motion of it is either up or down. Based on this, this wiper moves. Based on this, V0 is equals to applied voltage Vi into the resistance divided by the total resistance. Types of this resistive displacement sensors: translational, we discussed, and single turn and multi-turn. Helix type, heliport. This is for angular displacement. This is for translatory displacement. Heliport can be used for both to measure the angular and translatory displacements. Working principle of this: the motion of the object changes the effective resistance. The output voltage V0 changes. V0 is proportional to the displacement. Already we discussed. Based on the motion of the object, the wiper varies. Based on that, resistance varies. That means output is also varying. The output voltage is proportional to the displacement. These are the generally used potentiometers, or we can call pots. See, this is the wiper. and here, sorry, this is the wiper here, and this is the shaft. Here, this is the wiper, whatever we need to vary. This is completely the resistive element. Here, this is the resistive element. This is the wiper. Based on the wiper, the resistance varies. What are the advantages of potentiometric transducers means? It is inexpensive, cost is less, simple to operate. By simply varying the wiper, we can measure the displacement. Simple to operate. Useful for measurement of large displacements, and these potentiometric transducers can be used for measurement of measuring the large displacements. Electrical efficiency is very high, high efficiency, provides sufficient output to allow control operations. It is providing the required output with the control operations. Disadvantages of potentiometric transducers. What are the disadvantages means? Large force is required to move the sliding contacts. That means the required force to move the wiper is more. The sliding contacts can wear out, become misaligned, and generate noise. Noise problems will occur in this potentiometric transducers. What are the applications of potentiometric transducers? Used in control applications, used in error sensors, used to measure pressure and displacement. How to displacement is now discussed. So this can be used to measure pressure and displacement, as well as it is used in sensors, in error sensors, as well as the control application. Next is capacitive transducer. Right, what is a capacitive transducer means? Already it is a type of transducer, passive type transducer. But in this, how it is means, the variation of the capacitance is measured. That is depending on the displacement. Measurement of displacement, force, pressure. This capacitor transducers are generally used for measurement of displacement, force, and pressure. Measurement of liquids as well as gas levels also. Capacitor transducer is a passive transducer. How it is means, here the principle is the variation of capacitance is measured. That measure the capacitance value is depends on the measure value. Right, here these capacitive transducers are used for measurement of displacement, force, pressure, as well as the liquid levels or gas levels. See, this is the construction of a capacitor. We know that what is a capacitor means, two parallel plates, in between there will be a dielectric medium. Right, see, this is the length of the parallel plates. These two are the two parallel plates. Area of the parallel plate, this is the area of the parallel plate, and this one is the dielectric medium placed between the two parallel plates. Now this is a capacitor. See here, this dielectric medium can be moved towards or inwards in between the parallel plates. See, generally this is the area. Right, this is the change of the area because of the movement of the dielectric. See here, actually the plates are from here to here, but here it is, there is a movement in the dielectric medium towards right side. So the towards right side of D. So there is a change in the area, delta A. This is the variable length. Differential capacitive sensors. See, these two are the plates. Fixed center plate. This is the movable plate. This is the fixed one. This is the movable one. And the difference is here it is D minus X and this D. So this is the area of the capacitor. What is the principle of this capacitive transducer means? We know that the parallel plate capacitance is equals to the epsilon into A by D. C is equals to, what is a capacitor means? Capacitor is two parallel plates, in between a medium is placed, and the capacitance is measured. What is the formula for capacitance is equals to epsilon A by D. See, what is epsilon? Epsilon is the permittivity of the medium. Epsilon is the permittivity of the medium, that is for dielectric constant. What is the area? A is the area of the plate, area of the plate, and D is the distance between the plates. D is the distance between the plates, area of the plate, and epsilon is the permittivity of the medium. This epsilon is equals to epsilon naught into epsilon r. This already we know. Epsilon permittivity is equals to the product of the relative permittivity and the permittivity of the free space. So the capacitance C is equals to epsilon naught into epsilon r into A, area of the plate, divided by the distance between the two plates. So the units for the capacitance is farads. Here C is the capacitance. The units here are farads. See, based on this, that means from this equation, this by varying the area, if there is a change in the area of plate is directly proportional to the capacitance. Capacitance, that means the capacitance is directly proportional to the area and inversely proportional to the distance between the plates. If any one of this parameter is varied, that means the capacitance will be varied. This is the this principle is applied in these capacitive transducers. How it is, we will see. Change of capacitance is caused by the change in the area of plates and change in the distance between the plates. If any one of this parameter, either area of the plate or the distance between the plates is varied, means definitely the capacitance will be varied. Right. Change in dielectric constant. That means see epsilon permittivity of the medium. It is equals to epsilon naught into epsilon r, free space into relative permittivity. This relative permittivity will be changed based on the dielectric medium. That means by varying the dielectric constant also, dielectric medium also, this capacitance can be varied. That means the capacitance can be varied with A directly with area of plates, indirectly inversely proportional to the distance between the plates, and directly proportional to the dielectric constant. Now we will see the construction of a capacitive transducer. We know that it has two plates placed in parallel. See, in out of these two plates, one is the fixed plate, and the other one is the dynamic plate. That means it is movable. The capacitor has two plates. Out of these two plates, one is the fixed plate and another one is the dynamic, that is movable plate. And the diaphragm moves under the application of pressure or force. There will be a diaphragm that moves based on the applied force or pressure. Right. See, if you see the construction of the capacitive transducer, just now we discussed out of these two plates, one is fixed plate and another one is dynamic plate. That means static plate, this is the fixed one, and M is the deflected diaphragm. That means it is a movable plate. This one plate is fixed and one plate is moving. See, that means one plate is constant fixed plate, the other plate is moving. This other plate is moving means the distance between the plates is varying. And also the electric medium also varies based on this. See here, diaphragm static position. This is the static position. This is the deflected diaphragm M, and this is the dielectric, and this is the rear cavity, and static plate is placed in this, and this outer part is insulated supporting frame. See, based on the applied pressure, this diaphragm moves. Right? This is about the construction of the capacitive transducer. See, now we will see the working of this capacitive transducer. If the applied pressure increases, the pressure is increased, that means this pressure bends the diaphragm inwards, diaphragm inwards. That means if the diaphragm is inwards, the diaphragm is inwards. Here you can see if the pressure is applied, that means this pressure moves the diaphragm inwards to the frame, inwards to the frame. That means this dielectric medium is reduced, as well as the distance is also reduces. There will D increases. Hence, capacitance is also decreased. See here, we know that this distance and the capacitance is inversely proportional to the distance. Sorry. If pressure increases, the diaphragm bends inwards. With this, the D decreases. Distance between the two parallel plates decreases if the diaphragm bends inwards. If the D is decreased, C equals to epsilon into A by D. C is the capacitance is inversely proportional to the distance between the two plates. That means if the distance is decreases means obviously the capacitance increases. Capacitance increases. This is one case. In the another case, if pressure decreases, the applied pressure is less. That means the diaphragm pulled outwards. The diaphragm pulled outwards. If it is pulled outwards, means the distance between the two parallel plates increases. Distance is increased. The distance is increased means capacitance is decreases. The capacitance decreases. Right? That means by varying the distance between the plates, the capacitance can be varied. That means the D is increasing or decreasing depending on the applied pressure. This is the principle of the working principle of the capacitive transducer. Next, this capacitive transducer is a part of oscillatory circuit. If it is a part of oscillatory circuits, this changes causes a change in the frequency of oscillator. This change in capacitance changes the frequency of oscillator. Change in frequency is a measure of magnitude of the applied force. Applied force. That means if this capacitive transducer is used in this oscillatory circuits, there is a change in capacitance means definitely there will be a change in the frequency. X equals to 1 by 2 pi FC. Right. That means there is a change in the frequency. This change in frequency, the change in frequency, what is the change? This change in frequency is the magnitude of the applied force. That means here the applied force is reflecting on the frequency, change in the frequency in a oscillatory circuits. What are the advantages of this capacitive transducers? See, what are the advantages? It requires extremely small forces to operate. The required force is less, extremely small to operate the device, right? Inexpensive and easy to construct. Construction is easy. Only one plate is constant fixed plate, another one is a movable one. That means the diaphragm. Okay, that means easy to construct as well as inexpensive. Cost is also less. Extremely sensitive. Extremely sensitive. A small forces to operate. It only requires small forces. So the sensitivity is also very high. Good high frequency response. Frequency response of capacitive transducer is good. High input impedance. This is also another advantage of capacitive transducer. And resolution. The resolution of this capacitive transducer is of the order of 2.5 into 10 power minus 3. The resolution is 2.5 into 10 power minus 3. And another advantage is it requires small power to operate this capacitive transducer. The required power is very small. It requires small power to operate them. These are the advantages of capacitive transducers. What are those advantages means? Only it requires extremely small forces to operate, inexpensive and easy to construct, extremely sensitive, frequency response is good, high input impedance, the resolution is high, it is 2.5 into 10 power minus 3 and operating power is very less. And what are the disadvantages of this capacitive transducer? What are the disadvantages means? See, sensitive to temperature variations. This is the drawback of this capacitive transducer. And this is the same drawback of the semiconductor strain gauge. Sensitive to temperature variations. That means whenever there are variations in the temperature means, then definitely there will be variations in the output also. Possibility of erratic or distorted signals due to long leads. Due to the long leads, distorted signals, there are the possibilities of erratic or distorted signals. Low frequency response. For low frequency response, it is poor. Shows non-linear behavior. The behavior of this capacitive transducer is non-linear on account of edge effects. Due to the edge effects, there will be a non-linear behavior in this capacitive transducers. And what are the applications of this capacitive transducers? This capacitor already used. This can be used for the measurement of both linear and angular displacements. Capacitive transducers are used for both linear and angular displacements. Used for measurement of force and pressure. Just now we discussed how this pressure can be measured using this capacitive transducer. So it is used for measurement of the force and pressure, and also used for measurement of humidity in gases. Capacitive transducers also used for measurement of humidity in gases. Used in conjunction with mechanical modifiers for measurement of volume, density, liquid levels, weight, etc. Not only for force and pressure and humidity in gases, it also used for the measurement of volume, density, as well as liquid levels and weight, etc. These all are the applications of capacitive transducers. See, a summary of this session. What we discussed in the session means foil strain gauge. We discussed foil strain gauge. It is a type of strain gauge. On a thin paper, metal is placed, and this nichrome type of material is placed. And after that, the masking and etching will be done to get for the construction. Foil strain gauge, and another one is the semiconductor strain gauge. What is a semiconductor strain gauge? Means semiconductor material is used to measure the resistance. That means here there is no variations in the dimensions in the semiconductor strain gauge. Only the resistivity of the material varies based on the applied pressure. Next one is a potentiometric transducers. Potentiometric transducers. There are different types of potentiometric transducers based on this helical, helipod type, angular, translatory. These are there. Right? These potentiometric transducers, the resistance will be varied. That means there will be a wiper. That wiper is varied based on the applied displacement, displacement or. Right. See here, this angular displacement all can be measured in this potentiometric transducers. And the next one is the capacitive transducer. Just now we discussed capacitive transducer used for measurement of force, pressure, displacement, etc. And also we discussed the construction and working of the capacitive transducer, how this capacitive transducer is constructed, and also we discussed on the working of the capacitive transducer. Advantages and disadvantages of foil strain gauge and semiconductor strain gauge, potentiometric transducer, as well as the capacitive transducer. Each transducer has its own advantages, its own disadvantages, and also we discuss the applications of all these devices. See, that means overall in this session we discussed about the resistive transducers as well as the capacitive transducers. These two are this resistive transducer as well as the capacitive transducer. Both are passive transducers. Both are passive transducers. Right? Let us have some small few questions. Small case. In foil strain gauge, Dash material is used as strain material for construction. Dash material is used as strain material for construction. Foil strain gauge. Option A is mica, B iron, C nichrome, and D is the bakelite. What is the answer? C is the nichrome. Answer option. Nichrome is the material used in foil strain gauge. Second question, a semiconductor strain gauge having gauge factor of semiconductor strain gauge factor of value high value. Option A high value, option B medium value, option C low value, option D small value. Gauge factor, it is low value. Third question, a semiconductor strain gauge is a dash type of transducer. Semiconductor strain gauge. Option A variable capacitance, option B variable inductance, option C variable resistance, and option D variable voltage. Semiconductor strain gauge, it is a variable resistance type transducer. Next question, potentiometric transducer is dash type of transducer. Option A active transducer, B passive transducer, C voltage transducer, and D current transducer. Potentiometric transducer, it is a passive transducer. Next question, potentiometric transducer converts dash into dash. So option A is electrical signal into mechanical signal. Option B displacement into electrical signal. Option C force into displacement. Option D electrical signal into linear motion. So what is the answer? Potentiometric transducer converts displacement into electrical signal. Displacement into electrical signal. Next question. In a capacitive transducer, the movable plate is called as, option A dynamic, option B static, option C diaphragm, option D piper. So the movable plate here is called diaphragm. Next question. In a capacitive transducer, when pressure increases, what happens to the capacitance? What happens in a capacitive transducer if pressure is increased? That means it moves diaphragm inwards. That means distance between the plates decreases. So the capacitance, what happens to the capacitance? Here options are A decreases, B increases, C varies, D remains constant. That means option is capacitance varies. The capacitive transducers are also used for measurement of option A linear displacement, B force and pressure, C humidity in gases, D all of the above. What are the applications of capacitive transducers? That is here in the given answers, D is the answer, right answer, all of the above. So what are the questions we can expect from this topics means? We discussed about the potentiometric transducer. From the potentiometric transducers topic, we can explain the working and construction of potentiometric transducers and list the advantages and disadvantages of potentiometric transducer. It is in short answers, as well as also the applications of potentiometric transducers. List the applications of potentiometric transducers. That means these two you can expect in the short answers, these two in the long answers. And again from the other topics, explain the principle of capacitive transducer. What is the principle applied in the capacitive transducer? That is based on the capacitance formula C equals to epsilon A by D. By varying one of the parameters, the capacitance can be varied. See, and the construction and working of a capacitive transducer. List some advantages and disadvantages of capacitive transducer. List the applications of capacitive transducer, as well as we also discussed about the strain gauge, foil strain gauge, and the semiconductor strain gauge transducers. From this also we can expect the questions, that is construction of foil strain gauge, construction of semiconductor strain gauge, as well as the advantages, disadvantages of those, and the applications of semiconductor strain gauge. All these questions we can expect from these topics. right? That means, in brief, in today's session, we discussed the four topics, that is foil strain gauge, semiconductor strain gauge, potentiometric transducers, as well as the capacitive transducers. Okay, with this I'm going to end my session today's. Okay, thank you.